So I'm going to describe a couple of model selection problems. And these are only some examples, but there are many more of what we call model selection problems. A model selection problem is basically, how do you select the function f, or the model class, that maps your features x to your target y? Okay. So our overall goal is we're going to have some f of x that maps to y. And the model selection problem is just about selecting that f. Actually, let's clarify that this is f of xw. Okay. How do we choose that f? So we're going to look at a couple of examples, but there are many more examples. The first example is our polynomial example. So in the notes that I asked you to read before class, you learned about people using polynomial models to fit some COVID cases. And we said that you can kind of realize a polynomial model using our linear basis function in regression, right? And we said that the polynomial model has some degree d. Okay. The degree d is, let's say, what's known as like a hyperparameter. So it's not a parameter that we're going to fit using the ordinary least squares. So we have, let's say, these w's are parameters that we're going to fit using ordinary least squares. But then we also have this other parameter that's d that we can't fit that using ordinary least squares, but this d controls how complex our model is, right? We know that, let's say, a first order polynomial is very simple. A higher order polynomial is a much more complicated function. So this hyperparameter d controls how complex our model is. Okay. So the model order selection is a problem of choosing d. How should I go about choosing d? So suppose I decide to use loss function to select my model order. Okay. So I have some choices of d. So let's say maybe I'll make a list of d equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And for each d in the list, I'm going to fit the model of order d. So let's say I'll fit a model of order 1, then I'll fit a model of order 2, then I'll fit a model of order 3, etc. So I end up with many candidate models. Okay, so I end up with a, let's say, a candidate model 1 with one estimate of weights. Then I end up with a candidate model 2 with another estimate of weights. Candidate model 3 with another estimate of weights. And remember, these are not just, let's say, the same thing with different weights. It's different model complexity. So here I might have W0 plus W1x. Here I have W0 plus W1x plus W2x squared. Here I have W1x plus W2x squared plus W3x cubed, and so on. And of course, the weights that I fit are going to be different in each case as well. So I'm going to fit all of these different models, and then I'm going to compute the predictions on the training data for each model. And then I'm going to take that prediction, and I'm going to get the mean squared error for each model. So I have MSE1, MSE2, and then I'm going to choose a model order that has the lowest mean squared error. Is this a good approach to choosing the model order D? Okay, so Ben says it's not. Why not? So that's exactly right. So if you remember from this kind of intuition we had, and you'll formalize it when you look at those linear regression error decomposition notes I mentioned, we expect that the error for the training data is just going to keep decreasing with model complexity. So if we use this approach and choose the model with lowest training error, we're always going to choose the most complex model. But of course, the most complex model that we consider might also have high variance. So the loss function is always going to decrease with a d for the training error, but that won't necessarily give us the best error on the test data. It won't give us good generalization. So that won't exactly work. Now, before I tell you what to do instead, let's imagine a different example of a model selection problem. So a feature selection problem. Okay. I have some high dimensional data and target variable. So some high dimensional data. Here's a matrix. It's a very, very wide matrix. Okay, so it has many, many columns in it. I have x1, x2, all the way up to xd. Now, here's my problem. Many of these columns contain features that are not really relevant to the target variable that I'm trying to predict. Here's a target variable I'm trying to predict. Okay, so every row in this matrix is the sample, and I have many, many features and a target variable. Most of the columns are not relevant. I want to select a subset of features and use only a subset of features to train a linear model. Why use a subset of features? Well, if I use all the features, first of all, then I have many parameters and a more complex model. So I have a risk of overfitting. Also, if I have many features, we know that for a linear regression with the ordinary least squares solution, there is a unique solution only if this feature matrix is full ring. So we need, if the square matrix that we compose by taking the transpose multiplied by itself is full ring. So we need to have more samples and features. We need this n to be bigger than this d. Okay. So we want to select only a subset of features. So for example, choose this feature, this feature, this feature, this feature, train the model using those features and ignore all the rest. Okay. Can we use a similar approach where, let's say, we take different combinations of features, find the mean squared error for a fitted model using those features, and select the one that has the lowest mean squared error in the training set? So we'd have exactly the same problem if we did that. The more features we use, the more complex our model is because it has many possible parameters. And we'll end up overfitting, so kind of learning the noise in the training data, and end up with high test error. So what's an alternative? Does anyone know what we do instead? So we want to evaluate the test error. Let's see. Let's say we would, do something like this. Now, if we would just optimize for least test error, so let's say instead of computing this MSE on the training data, we compute the MSE on the test data. This wouldn't exactly help because we'd still be, let's say, kind of potentially overfitting to the test data. And we wouldn't necessarily realize we were doing this because then we're left without any held out independent data on which to see if our model generalizes. But we could do something similar to that. So instead of dividing our data into training and testing, we're going to divide it 3 ways. So we'll have training, validation, and test. Okay. Now for each candidate model, so for each of, let's say, F1, F2, F3, I'm going to fit the parameters using the training data, but then I'm going to compute the mean squared error on the validation data. And then I'll choose the model that minimizes the error on the validation data. Now, I don't want to stop there because I want to see how my model performs on new unseen data. So the validation data is no longer unseen data because I use my validation data to choose D. So I can't use it to evaluate the model anymore. But I still have this test data. So then I'll use the test data to evaluate the model. So to summarize, I split my X, Y into training, validation, and test. Then I loop over all of my candidate models. So I have up to P models. For each candidate model, I find a fitted model. So I find the parameters that go with the fitted model P. Then I find the predictions of that fitted model. And then I get a score for the fitted model. But the score is over the validation data. Okay, so notice that I'm fitting using training data, but I'm scoring using validation data. Now I have a score for each candidate model. So for every P, I have a score. And now I'm going to select the model order with the best score on the validation data. And here I'm assuming that, let's say we're using mean squared error for the score. If mean squared error is the scoring metric, then we want the model order that has the lowest mean squared error. So I'm going to choose a value of P that minimizes the score, meaning that has the lowest mean squared error. Okay. Finally, I'm going to evaluate my model over the test data. So this data was not used to find W, and it was also not used to find P. Okay. It's a new independent set of data. And that's what I'll use to get a sense for how well my model did. So I'm essentially dividing the data into one part used to train for W, one part used to train for P, or model order selection, and one part used for evaluation. So this could be a reasonable approach. What are some problems with this approach? It's not the worst thing ever. So the worst thing ever is to train and test on the same data, or to use the test data to, let's say, choose a model order. Those are both bad because then you don't have a new held out data set for evaluation. So this is at least better than that approach. But there are still some problems. Problem number one is, well, if you have limited data, then your parameter estimate error is increasing because now you have less data with which to estimate the parameters. So we're using some of the data. Here, let's draw this. Okay, so we have, this is all of our data. We're going to use some of it for training, some of it for validation, and some of it for testing. Okay. So since I'm reserving some of my data for model selection, I only have a little bit of data left to train the parameters. So that's not so good. And it's especially bad for problems with a small number of samples. And essentially, our fitted model is going to vary a lot depending on which samples happen to have been selected for training and validation. So we saw from our previous discussion that, the particular selection of training points can influence the fitted model a lot. That for different selections of training points, you can get very different models. And if you use this very simple training validation split, that same thing can happen where your fitted model is very dependent on which samples you select for training and validation. Evan asked whether this is also a problem for classification problems. Absolutely. It's a problem for all machine learning problems. So the simple split is kind of acceptable, but it doesn't yield the best results if you have a small number of samples. So as an alternative, we have what's known as k-fold cross-validation. Let's look at k-fold cross-validation instead. So I'm still dividing my data into a training and a test set. But then I'm going to further divide my training data. And I'm going to actually divide my training data multiple times. So let's say 3 times, but it could be any number. I'm going to divide it 3 times, where each time I dedicate part of the data to be used for validation. And I make sure that there is no overlap. Okay. So the first time, this first part of the data is used for validation. The second time, this part of the training data is used for validation. And the third time, this part is used for validation. Okay. So notice that I'm using all of the training data eventually to fit the models. And I'm using all of the training data also to validate the models, but never at the same time, right? We understand why it doesn't work to do it at the same time, because the training error will always decrease. Okay. So I'm going to have 2 loops now. Okay. In the outer loop, I'm going to loop over what's called each of these folds. Okay. So in the outer loop, I'm going to, let's say, have one instance of training using this split, where the purple is training data and the blue is validation. One instance like this, and one instance like this. Okay. Now imagine we're looping, we're inside the loop, and in our current iteration of the loop, this blue part is validation data, the purple part is training data. Okay. And inside the loop, I'm going to have an inner loop that loops over all of my candidate models. So we had all these candidate models up here. So I'm going to evaluate all these candidate models, and I'm going to fit the candidate models over the purple data, the training data. And then I'm going to score each candidate model using the validation data, so the blue data. So what I'm going to end up with is, let's say for each model candidate, let's look at this example. I'm going to have W, I, P. Okay. That's trained on the purple data, each instance. And here I is the fold. So I have I equals 1. I equals 2. Okay. So here I have, let's say, W11, okay, where, let's say, the second index is the model order. And I might have W12, W13. So for every candidate model, here I have 3 candidate models. I'm going to use the purple training data to fit some weights, or to, and then I'm going to derive some scores. The scores are going to come from the validation data. So I'll have the score in iteration 1 for model 1, the score in iteration 1 for model 2, and the score in iteration 1 for model 3. Okay. And again, these all come from that blue validation data. Then I'll do the same thing in iteration 2. So the next time through my outer loop, I'm going to fit all of the candidate models and then score them on the validation data. But this time I have slightly different validation data. So the first time through, my training was on this purple data. So the W's come from the purple data and the scores come from the blue data. And the next time through, the W's come from this other purple data and the scores come from this other blue data. finally, in my third iteration, I'm going to derive fitted models and then score them on validation data using this alternative split. So for each candidate model, I now have K scores. Let's take those scores. And let's say now my overall score for model 1 is going to be the mean of S11, meaning the mean score of model 1 for fold 1, model 1 for fold 2. Okay, so here the first index is the fold, and model 1 for fold 3. So I'm going to take the mean. Let's put this up here. And then I'll compute this for each of my candidate models. So I'll have a mean score for the model order 2. And a mean score for model order 3. And then I'll select the model with the best mean score. Okay, so let's say model 2 has the lowest mean squared error. I'm going to select the model order 2. And finally, I'm going to evaluate it on this test set. The test set was never used yet. The red set, I haven't looked at it at all. So when I evaluate model 2 on the test set, I get a good idea of the generalization error. So this is cross-fold validation. Are there any questions? Okay, I'm just going to introduce 2 little complications and then we'll stop for today. Complication number 1 is how to split my data. Okay. So imagine I have some data I've collected. Okay, let's think. I have okay, so I've collected some data from let's say I'm collecting student exam scores. Okay, and I have student exam scores from multiple exams, and I'm interested in predicting exam scores using as input, let's say, some characteristics of a student, maybe how many hours a week they study. Okay, so I have a list of data that looks something like this. Okay, so I have student 1 score on exam 1, student 2 score on exam 1, student 3 score on exam 1, okay, so on. Okay, and then I also have student 1 score, student 2, all the student scores on exam 2, and so. Okay, how should I split up this data into, let's say, training, test, and validation? So let's say actually this is all training data. Maybe I have different data I've already held out for test. How should I split up this data using k-fold cross-validation? One option is to take all this, okay, and say in the first fold, use, let's say, this as the validation data. In the second fold, use some other subset in here for validation data. And in the third fold, use this subset here for validation data. Is this a good approach? Michael says they come from different distributions. What do you mean by that? So if I split up the data like this, then all of the data in fold 1 is going to come from exam 1. All of the data in this purple fold will be from exam 2. Is that a good thing? Okay. Well, it's a little tricky. It depends on exactly what I'm trying to learn. But it might not necessarily be good for the data in the validation set to have, potentially very different characteristics from the data in the training set for that iteration. So what's a solution to this problem? Well, one very easy solution is just to shuffle all the data, exactly. So this is what's called a shuffle split. So here, if you look at this data, where you can imagine each exam as a group. Okay. So the default k-fold cross-validation, imagine each exam as a group. So I have 100 samples, and they're ordered so that the first 10 belongs to group 1, the second 10 belongs to group 2, and so on. If I just split it using the default k-fold, right, then each validation set will include some groups, but not other groups. Alternatively, I could shuffle it. So if I shuffle it, then you can see the red data here is the validation data. If I shuffle it and then split it, then the validation data in each fold will include representation from many different groups. Okay. So if I want kind of a random selection of groups, then this might be a good way to do it. Now, there are some other potential problems here. So, okay, imagine I have something like this instead. So I have, let's say, student 1 scores, student 2 scores. So now my data is ordered like this. And I have a concern here that I might be overfitting to particular students, right? So let's say there's one student in the class who happens to be a very strong student, but who only studies for 20 minutes a week. Okay, maybe the student already took machine learning. And I have this concern that my model might be kind of overfitting to examples like that. So learning individual students instead of learning a general relationship between, let's say, study time and exam scores. So I want to solve this by making sure that my validation set only includes, let's say, okay, I want to solve this by making sure that every individual student is either represented in the training data or in the validation data, but never both. So if I'm concerned that my model is maybe overfitting to individual students, then I would want to make sure that, let's say, my validation data doesn't include students I've already seen in the training data. So in that case, what I want is to make sure that each group is either in validation or in training, but not in both in a particular fold. So then I would use what's known as a group k-fold, where each time I select training data, okay, it's still kind of distributed from among the entire set of samples. So it's not only the samples from the beginning, then the second group, then the third group, but I made sure that each group is only represented in one part or another. Okay. Now, that was maybe a good approach for this predicting student exam scores. But let's say I have a different data set. Let's say my data set is spam email. I'm trying to predict whether an email is spam or not. Okay. And maybe the first 50 samples in my data set are spam. The next 20 samples are marketing emails, but that I signed up for, so not spam. And the last 30 samples are personal emails. There's another example where using k-fold cross-validation would work poorly. So imagine here that, let's say, the spam characteristic is a class of the data. It's a thing I'm trying to predict. Okay. if I, let's say, just use k-folds naively like this, then maybe in the first iteration, all of the spam emails in my validation data and none of the spam emails in my training data. That's obviously very bad, right? Whereas in the last iteration, I have the reverse situation where all of the spam emails in my training data, but none of it is in validation. What I want is to have kind of the same distribution of the target variable in my individual folds as I do in the overall data set. So in order to achieve that, we use what's called stratified k-fold. In stratified k-fold, the folds are selected so that, again, what all of these have in common is that you never have the same data used for validation more than once. Okay, so that's common to all of them. But in stratified k-fold, each validation set has the same distribution for the target variable as the overall data set. So you can see, let's say here, each fold, each validation fold in red has a little bit of the blue class, then a little more of the tan class, and still more of the brown class. And that's the same as the overall data set. Now, a final kind of, let's say, split is a time series split. So if you remember when we talked about data leakage, we said that it's very important not to predict from the future. Right? Predicting from the future is an example of data leakage because you're using data that's not available to your model at prediction time. What if you have time series data? So samples 0 to 100 are time series samples, where sample 0 happens first, then sample 1, and so on. If you would split it using, let's say, standard k-fold, then when you do the validation, let's say for validation set 0 here, your validation is over data trained using data in the future from validation set 0. So the time series split makes sure that in each fold, the validation set comes after the training set. Now, this is just a very quick overview, but this is a very important and often neglected point. So selecting the right fold is very important for avoiding data leakage and making sure your results are valid. Okay, there's one more very quick complication to introduce. Now, in our previous discussion, we said we're going to just choose the model with the best score. And here we're assuming mean squared error as a score. So choosing the model with the lowest mean squared error. The problem is that if we do this, we often actually end up still overfitting a little bit. So there's a heuristic that's known as the one squared error rule. Okay, and we're going to use this one standard error rule. And we'll use a one standard error rule to select a model that might not necessarily have the best mean squared error for the validation set, but often generalizes a little bit better. Okay, and here's how it works. So you have some data, you divide it into your k-folds. You compute your scores for each model for each fold. Okay, so these scores here. And then you compute the mean scores for each model. Okay. And in addition to computing the mean score, which is, let's say, S bar of P, you'll also compute the standard deviation of the scores. So remember, you have k scores for each model. You can compute the mean of them, and you can also compute the standard deviation of the k scores. And then you compute the standard error like this, which is just the standard deviation over square root of k minus 1. Now, when you do that, you'll get, let's say, something like this. I'm going to draw this. Okay. So imagine we have these three errors, these three models. This is P, so the model complexity. And this is score, so the basically mean squared error. Now, imagine we have some models that look like this. Okay, model 1, model 2, model 3. Now, actually, sorry, other way around. If we were choosing based on score alone, or mean score. So these are the mean scores actually. Right. So maybe for the first model, I got this over 3 folds. Right. These are the individuals. If I would choose based only on the mean squared error, then I would choose this model right there. But actually, in truth, if I look at maybe the individual scores over which the average is computed, maybe I think that these two models actually have very similar performance. And this model might actually be a little bit overfitted. So I'm going to compute a standard error for the mean, where for each mean, I'm going to compute some error bars that look like this. Okay. So the error bars go mean plus 1 standard error to mean minus 1 standard error. Next, I'm going to define a target. So the target is at the optimal value. So let's say the minimum mean squared error. So I have 3 models I've considered. For each model, I compute the mean and the standard error of the mean. Then I find the model with the best score. Okay, so this is a model with the best score. And then I set a target score. Sorry, I drew this in the wrong place actually. The target score is the score that's, let's say, I'm going to draw it like this. Okay. My target is to have a model that's as simple as possible, that's within 1 squared error of the mean. So according to this rule, which model should I choose? Let's try and say that again. So I compute the mean and the standard error for each model. And then I'm going to compute a target score. A target score is a score that's within 1 standard error of the model with the best score. So this entire range in here is my target range. And now I want to select the simplest model that's still within my target range, which is the simplest model in my target range. Okay. So here, the models are increasing in complexity from left to right. So the simplest model in my target range is model 2. So this is so model 2 is going to be the one I select according to the 1 squared error rule. So this heuristic is basically an acknowledgement of the idea that the optimal model according to mean squared error on the validation set might still be slightly overfitted. In addition to that, there might be models that are simpler but have comparable error. So in order to find the simplest model with comparable error to the best model, we look for the model that's simplest but within 1 standard error of the mean of the best model, and then we choose that model. Okay, we're going to stop here for today. We're not going to get to regularization this week. And I'm going to see you again on Thursday. And on Thursday, we'll kind of try and get a better intuition for this with a lot more examples. And we'll also finish our case study from last week on Thursday. All right, take care. See you all then.